You know, sometimes the most fascinating stories are hidden in plain sight, just tucked away in university archives. Today, we're going to crack open a master's thesis from all the way back in 1976 to uncover a brilliant piece of practical, problem-solving engineering that really, quietly, changed the game.
All right, here it is. Modernization of a Portable IDC Test Set. This is the final report by a guy named Donald D. Marsh for his graduate engineering program at Texas A&M. And look, this isn't just some old paper. It's a window, a total time capsule into the challenges and the technology of the mid-1970s. And that was a time of incredible transition in electronics.
So what was the big problem Marsh was trying to solve here? Well, it really boils down to this one number, 50 pounds. That was the weight of the so-called portable test set he was tasked with improving.
Yeah, that 50-pound weight belonged to this thing, the Instrument Data Converter Test Set. It was an essential device, right? It was designed to simulate a central computer for testing remote radar sites. But its biggest problem wasn't really technical, it was physical.
And Marsh himself just put it perfectly. The 50-pound maximum weight requirement, he said it simply wasn't a stringent enough specification. I mean, it's a classic case of something working on paper but totally failing the test of human reality. This wasn't just an inconvenience, it was a fundamental design failure.
So besides just feeling like you were lugging around a bag of concrete, what was actually wrong with this machine? Well, Marsh's thesis breaks it down beautifully, identifying 3 key villains that he needed to conquer.
Okay, so here they are: weight, cost, and noise. That $5,000 price tag in 1976, that's like over $25,000 today. And the device was so sensitive that something as simple as a power drill on the same circuit could corrupt its data. So what you have is a heavy, expensive, and super finicky machine, and that's our starting point. And the investigation pretty quickly pinpointed the main culprit for both the weight and the cost, the data modem. The original, this Lenkerd 26C, was an absolute beast, weighing over 20 pounds and costing more than $4 grand. It alone accounted for almost half the weight and a whopping 80% of the cost. Marsh found a newer model, the 261A, that was just a total game changer. The key insight here was that one single component swap could solve 2 of the 3 big problems right off the bat.
But that still left that third, more invisible enemy, electrical noise. And this was a critical issue because it could introduce errors, making the whole test set completely unreliable. I mean, you can't trust a test device that might be giving you bad data.
And the thesis itself, it shows us the smoking gun. This is an actual oscilloscope reading of the system's master clock signal. See that nice clean square wave? Now look at those fuzzy spikes just kind of riding on top. Marsh measured those spikes at 0.7 volts of unwanted noise. Now that might not sound like a lot, but in the world of 1970s digital logic, that was a giant. To understand why that 0.7 volt spike was so dangerous, you gotta understand something called noise margin. Think of it like a circuit's defensive wall. The old system used a logic family called TTL, and its defensive wall was only 0.4 volts high. That 0.7 volt noise spike could easily just leap right over it, flipping a 0 to a 1 and corrupting the data. The result? Total chaos.
Now this is where Marsh's engineering solution gets really elegant. He proposed switching to a newer technology for the time, CMOS, which stands for Complementary Metal Oxide Semiconductor. Its key advantage? It had a much bigger defensive wall, over 1 volt high. That 0.7 volt noise spike just couldn't get over it. Problem solved.
Of course, engineering is all about trade-offs, right? CMOS was a clear winner on noise immunity, and it also used way less power, which helped reduce the weight even more. But there was a catch. It was significantly slower than TTL. For this application, though, where the top speed needed was only about 1 megahertz, that was a perfectly acceptable sacrifice. A really smart call.
So with a lighter modem and a more robust logic family selected, Marsh could now lay out the blueprint for a completely redesigned, modernized test set.
I know this looks complex, and it is, but what you're really seeing here is the new heart of the machine. This is the transmitter block diagram, the master plan for how all those new CMOS chips would work together to generate the test signals. This is the blueprint for a smarter, lighter, and much more reliable device.
And here's how that complex brain would actually be packaged. On the left, you see a new, smaller, purpose-built enclosure, and on the right, the redesigned front panel with all the switches and lights the operator would need. This is what takes the design from an abstract schematic to something you can actually picture a technician carrying out to a radar site.
Oh, and I love this detail. Marsh even considered the manufacturing process. This graph here compares the cost of two methods, wire wrapping, which is done by hand, versus creating printed circuit boards, or PCBs. See, for a large number of units, PCBs are cheaper. But for small batches, wire wrapping is actually more economical. His practical recommendation to stick with wire wrap, it just shows an engineer thinking about the entire life cycle, from design all the way to the budget.
So when you put it all together, this thesis is so much more than just a redesign project. It's a perfect snapshot of a specific moment in engineering history.
Just think about that. The CMOS technology that is the foundation of every single smart device we own today was, as Marsh noted back in '76, still in its infancy. He was an early adopter, recognizing its potential to solve a very real, very heavy problem.
And then, amidst all the diagrams and equations, there's this, the acknowledgments page. A special thanks goes to my wife for typing this report and correcting numerous spelling and punctuation errors. It's just a wonderful reminder that behind every technical document, there are real people, there are families, and a whole lot of human effort.
And finally, his conclusion. It's not a declaration of final victory. Not at all. It's a humble, honest assessment. He solved the core problems, but then clearly lists the next 5 areas that need more investigation. And this is the true spirit of engineering, right? It's an iterative process, always looking for the next improvement.
Donald Marsh's thesis took on a 50-pound problem with a new modem and an infant technology, and he left behind this clear, elegant, and very human story of engineering. It really makes you wonder, doesn't it? How many other stories like this are just sitting on a shelf, waiting for someone to open them up?